Let's do a simple example of correlation coefficient computation. Again, we have the same distribution here. We have the marginals computed. And if you compute the covariance by, well, first of all, this part is the correlation, okay? I omitted the zero, the outcomes that would lead to product of zero. You have 0 times this probability plus 0 times this probability. I didn't have much space here, so I omitted them. You have 1 times 2, this probability, 1 times 5, this probability, okay? 4 times 2, this probability, and 4 times 5 times this probability. That is the correlation, okay? Minus, you have the product of the means, and it turns out to be 0. No surprise here because, well, we know that they are independent from last week, right? The joint PMF here is given by the product of these two. So since they are independent, the covariance turns out to be 0, which means the correlation coefficient is also 0. Therefore, they are also uncorrelated. No surprise. Let's change this distribution a little bit. Okay. Now I have just swapped these two probabilities here. That's the only thing I did. Now, what this leads to is dependent random variables here. X1 and X2 are no longer independent. So let's find the correlation coefficient. First of all, I'm going to need the means, and the means are computed. Well, the marginal of X1 stays the same, because if you look at from this side, see the sum of these two doesn't change, so marginal of X1 doesn't change, but X2 is now different. So the mean of X1 is 1.5 as earlier, but the mean of X2 is now 3.62. Then let's compute the second moments, and these are the values you get, and then compute the variances by subtracting the square of the means from the second moments, and these are the variances of X1 and, well, sorry, this should be X2. And then we compute the correlation coefficient by first computing the covariance, and this part again, as you see, is the correlation. Again, I omitted the terms with 0 products. I get 1 to this probability, sorry, this probability, 1, 5 this probability, 4 to this probability, and so on. You get this result, and then I need to scale this by the standard deviations, and these are the variances. Therefore, the correlation coefficient turns out to be negative 0.178 something. Okay, so this is how you compute the correlation coefficient. You would need to compute the covariance and also the standard deviations, which means you need the variance of each component. And to compute the variances, you also need the means and probably the second moment. But this is how you compute correlation coefficients. Now, correlation coefficient is tricky to work with in the sense that when you know the correlation coefficient and you know how they affect each other, but well, you know how much they affect each other, you do not know how precisely. Okay, so this is a figure taken from Wikipedia actually, and it demonstrates that very different dependence relations might lead to the same correlation coefficients. So for instance here, well, on the top row, you have several correlation coefficients. So you see this is correlation coefficient of 1, a perfect linear relationship, and -1, it's again perfectly linear, but with a negative slope. So one increases, the other decreases. And here you have a high correlation on these ends. Okay, and here you have small correlation, 0.4, and here you have no correlation at all. But these are not the only cases. When you have the correlation coefficient, this shouldn't be what automatically comes to your mind. First of all, when you have the correlation equal to 1 or -1, you have no idea about the slope of this line. Okay. It could be large, it could be small. You do not have the exact relationship between the two. Okay, so you just have you just know that they are highly correlated, but you do not know the nature of their relationship. And on the third line here, you have the other side. You have no correlation at all, but you have no idea about the relationship itself. You see, it could be something quite well defined like this one. Okay, so we have some sort of functions that we can observe, like second order dependence and something like this here. We can even have clusters of data points, and therefore what I'm trying to say is correlation coefficient by itself, it says something. Yeah, it gives you an idea about how one component varies with respect to the other, but it doesn't really tell you the whole story. Okay, be careful about this. We have this quite famous data set, which is due to a statistician called Anscombe. This is famously called Anscombe's quartet. Okay, we have 4 distinct data sets, and they have the same definitive statistics. Okay, they have the same mean of x, mean of y. So when you compute with the mean with respect to x, each of them have the same value. If you compute the mean with respect to y, each of them also have the same value. They have the same variance with respect to x, the same variance with respect to y. Now we are talking about sample variance because this is not a distribution, but just data. But also they have the same correlation between x and y and the same linear regression line. So this relationship defining the correlation between the two. But as you see, the nature of the relationship is very different in each case, right? So this is sort of random here, but this doesn't seem random except for this single outlier, and this one here even more. And here we look like it looks like we have a dependence between the two. Okay, so you have to be very careful about these considerations. Another example, a great example is I have taken this from a blog where you have the link here, and you have very different scenarios here with 0 correlations and 0.5 correlations. I definitely recommend you go here and check it out because, well, you see, well, here 0 correlation could mean a scatter plot like this one, or maybe it's very closely related, but one single outlier, okay, it gives you a correlation coefficient of 0, or maybe it could be something like this. There might be a pattern to it, or you might have a functional dependence like this, okay, or you might have clusters like so, okay. So just depending on correlation coefficient itself, it could be misleading. And here, for instance, you have again clustering. And here, this is a very interesting case. Here, you see the blue line is the linear regression line. So it suggests a positive correlation, as we see 0.5 here. But you see we have 2 distinct clusters here with, I don't know if you see the red lines, but you see they have negative slopes. So the 2 subclusters, they are in fact negatively correlated. So correlation coefficient by itself in this sense could be misleading.